This is Lesson 9 in our Calculus 2 series, Indeterminate Forms and L'Hopital's Rule. This lesson is about limits of indeterminate form, and so we're going to start with a couple of examples that you already know how to deal with, and then we'll go from there. So recall that for limit as x goes to 2, x squared minus 4 over 2 minus x, the first thing we try to do when we evaluate any limit is plug in this x value. When we try that here, we realize that we get 0 over 0. Now, 0 over 0 is an indeterminate form. It means we need more information to see what this limit will be. So we factor here. In our numerator, we get x minus 2 times x plus 2. And we recognize that if we factor out a negative sign from the denominator, we can then cancel the x minus 2's, and we're left with x plus 2 over negative 1. So the limit as x goes to 2 here is the same as the limit as x goes to 2 here, and that equals the limit as x goes to 2 of x plus 2 over negative 1. And at this point, now that we got rid of the 0 over 0 situation, we can just plug the 2 in and we get 4 over negative 1 or negative 4. And that's our limit. We've also seen something like limit as x goes to infinity, 5x squared minus 4 over x minus x squared. Here, as x goes to infinity, we know that the behavior in the numerator is going to be governed by its highest power, that's the x squared, and the behavior in the denominator is going to be governed by its highest power, and that's a negative x squared. And so we're going to have infinity over negative infinity. Infinity over infinity is another indeterminate form. Again, it means we need more information. So in this case, we divide by the highest power we find in the denominator, which is x squared. So from here, we multiply by 1 over x squared over 1 over x squared. We distribute that 1 over x squared through and simplify. And then we take our limit, because we know limit as x goes to infinity, 1 over x is equal to 0. And limit as x goes to infinity, 1 over x squared is equal to 0. So this is going to 0, and this is going to 0, and so our limit is 5 over negative 1, or negative 5. Now you might remember rules here for limits with rational functions. When we're taking limits as x goes to positive or negative infinity, and you have the highest powers being the same in the numerator and the denominator, that's what we have here, then our limit is going to be the ratio of the coefficients. So our highest power is 2 here, it's an x squared in both numerator and the denominator, so that's the same. And so we're looking at the ratio of the coefficients. And so we're looking at the 5 and the negative 1. And so that's a negative 5. When we have the highest power greater in the denominator, we have an x to the 5th in the denominator, and we have only an x to the 1st in the numerator, our limit is going to be 0 as x goes to positive or negative infinity. And we find this limit the same way we did above here. When we have the highest power greater in the numerator, our limit's going to be positive or negative infinity, and we have to go through the details for the individual problem. So in this case, if we have limit as x goes to infinity, say 5x squared minus 4 over 1 minus x, we see the highest power is greater in the numerator than it is in the denominator. So again, we're going to divide by the greatest power that we have in the denominator, so that's x to the 1st. So we have multiply here by 1 over x over 1 over x, and simplify. And what's happening here, as x goes to infinity, this is going to 0, this is going to 0, and now as x is going to infinity, we have 5 times infinity over negative 1, and so that's negative infinity. So when the highest power in the numerator is greater than the highest power in the denominator and x is going to positive or negative infinity, you're going to get a limit of positive or negative infinity, but you just have to go through the details here. So you might have remembered these rules from what you've learned about limits in the past. But now we're going to build on this, because what happens if we have problems like this? Here we have limit as x goes to 0, sine x over e to the 4x minus 1. Now, we always try just plugging in this value first. So that would give us sine of 0 over e to the 0 minus 1. So that would be 0 over 0. Again, this is an indeterminate form. That means we need more information. But we can't use either of the tools that we just saw above. We can't factor here, and this isn't a rational function. So we need another tool to help us solve this kind of limit. Similarly here with x going to infinity, we know that as x goes to infinity, ln x goes to infinity, and also x is going to infinity, but again, this is an indeterminate form. Because here we need to find out if the numerator or the denominator is going to infinity faster, and how much faster. If the numerator goes faster, then this limit could be infinite. If the denominator goes faster, this limit could be 0. Or if the rates at which they go to infinity are in proportion, this could turn out to be a constant value. So we need more information about this as well. And we can't use either of the tools we saw above. So L'Hopital's rule is going to help us with these limits. Now keep in mind that L'Hopital's rule is only for limits with indeterminate forms of the type 0 over 0 or infinity over infinity. It will not work on any other kinds of limits. And L'Hopital's rule says, for f and g differentiable functions with g prime not equal to 0 near x equals c, if limit as x goes to c of f of x is equal to 0 and limit as x goes to c g of x is equal to 0, that says we have a 0 over 0 situation here. Or if limit as x goes to c f of x is positive or negative infinity and limit as x goes to c g of x is positive or negative infinity, that means we have an infinity over infinity situation here. Then L'Hopital's rule says that these two limits are the same. So we could take the limit of f prime of x over g prime of x, and that'll give us the same limit. Now keep in mind here, this is not a quotient rule. We're not taking the derivative of this quotient. We are taking the derivative individually of the numerator and of the denominator. So L'Hopital's rule says that we can evaluate this limit by taking the derivative of the numerator function, taking the derivative of the denominator function, and computing this limit instead. And here, when I'm saying c can be positive or negative infinity. So this also holds when x is going towards not just a constant number, but positive or negative infinity. So let's take a look at the examples that we saw above. Limit as x goes to 2 of x squared minus 4 over 2 minus x. We plug in 2 and realize that we have 0 over 0. That tells us we can use L'Hopital's rule. So we take the derivative here, that's going to be 2x minus 0, or 2x. The derivative here is 0 minus 1, negative 1. Now we plug in x equals 2, and we get 4 over negative 1, or negative 4. That's the same answer that we had above. Similarly, x is going to infinity, 5x squared minus 4 over x minus x squared. We recognize that this is going to be infinity over negative infinity, so we can, in fact, use L'Hopital's rule. So we take the derivative of the numerator, and that's 10x. The derivative of the denominator is 1 minus 2x. And now we take limit as x goes to infinity. But what happens here, we realize that we still have infinity over infinity, right? We have an infinity over a negative infinity here. So we use L'Hopital's rule again. The derivative of 10x is 10. The derivative of 1 minus 2x is negative 2. Now this is a negative 5, and so of course the limit as x goes to infinity of negative 5 is still negative 5. And that's the same answer we saw above. But now we can use L'Hopital's rule to solve the problems that we were looking at above that we didn't have tools yet to solve. So now we can solve limit as x goes to 0 sine x over e to the 4x minus 1. Again, the first thing we do is try to plug in 0, and when we recognize that we have 0 over 0, we realize we can use L'Hopital's rule. So we take the derivative here, and that's cosine x. Our derivative here is 4e to the 4x. And now we plug in x equals 0. So we have cosine of 0 over 4e to the 0, and that's 1/4. Notice here, every time I use L'Hopital's rule, I'm putting an LH over my equal sign. I've done that in all of the problems. I encourage you to do the same because it helps your reader to know how you got from this side of the equal sign to this side of the equal sign. So please go ahead and do that every time you use L'Hopital's rule. And let's take a look at this example as well. Limit as x goes to infinity ln x over x, we recognize that this is going to be infinity over infinity, and so we can in fact use L'Hopital's rule. So we take the derivative of ln x, which is 1 over x, the derivative of x is 1, and now as x goes to infinity, we have 0 over 1, and so this is 0. So now I'd like you to take a couple minutes and work on this limit. Limit as x goes to 0 of sine x over x. Don't forget to check that L'Hopital's rule does apply. The first thing you should always do with your limits is try to just plug in the number. So please pause the video and work on that. So the first thing we do is plug in x equals 0, and we see that we have 0 over 0, so we can and should use L'Hopital's rule to continue. So I have equals here with my LH, limit as x goes to 0, this becomes cosine of x over 1. And now we can plug in x equals 0, and so this is 1. Now let's take a closer look at what this is saying. As x is going to 0, we knew that sine x was going to 0 and x was also going to 0, but we didn't know which one was going faster, or if they were going at the same rate. That's why we had to do some more work. That's what makes this situation an indeterminate form. Finding that this limit is equal to 1 says that sine x is going to 0 and x is going to 0 at the same rate. They're going to 0 at the same rate. So let's take a look at what's happening here with y equals sine x and y equals x. As x is going towards 0, from both sides, notice that sine x and x go to 0 at the same rate. They have the same slope here. In fact, y equals x is the tangent line to y equals sine x at x equals 0. So they're going to 0 at the same rate. And that's how we can interpret this limit being equal to 1. Now let's take a look at limit as x goes to 0, tan x minus x over x to the third. Please pause the video and work on this. We start by plugging in x equals 0, and so we get tangent of 0 minus 0 over 0. Tangent of 0 is 0, so we end up with a 0 over 0 limit. And that's one of the types for which we can use L'Hopital's rule. So we take the derivative of the numerator, that's secant square x minus 1, and the derivative of the denominator, that's 3x squared, and then we again plug in x equals 0. Secant of 0 is 1, so secant squared of 0 is 1, and this is 1 minus 1 over 3 times 0 squared. Again, we get 0 over 0. So again, we use L'Hopital's rule. Taking in the derivative of the numerator, remember we have to use the chain rule here. The 2 comes down in front. This becomes 2 secant x to the first power times the derivative of secant x, which is secant x tangent x. And in our denominator, we have 6x. So we plug x equals 0, and again, we get 0 over 0. So we use L'Hopital's rule one more time. Limit x goes to 0. Now we've got to use the product rule here and the chain rule. So before doing that, I simplify this to secant square x, and then we use the product rule here. I factored out my original 2 outside of the entire thing. So we have the derivative of secant squared x times tangent x here, and then we have secant square x times the derivative of tangent x. And now as we plug x equals 0, we know we're going to get somewhere because our denominator now is just 6. So we just have to compute the numerator, and we find that is 2 times. Here we have 0 plus 1, so this becomes 2/6 or 1/3. Just remember as you're going through these kinds of problems that you can only use L'Hopital's rule when you have 0 over 0 or infinity over infinity. Let's take a look at another problem. Please pause the video and work on this one. Here, as x goes to infinity, e to the negative infinity goes to 0. And in the denominator, we have 2 times infinity. So actually, this is 1 over infinity, which is 0. We cannot use L'Hopital's rule. So I hope you didn't fall for my little trick there. I see students quite often trying to use L'Hopital's rule where it doesn't apply. So we always have to try to compute our limit directly before approaching L'Hopital's rule. So here we had 1 minus 0 over infinity. That's just 0. That is a determinate form, and so we're not using L'Hopital's rule. Let's take a look at another example. Here we have limit as x goes to 0 from the right of x squared times ln x. Now, one thing I want to point out, often when I see a one-sided limit, I'm kind of curious why. So I'm looking at this and I'm thinking, why do I need to have x going to 0 only from the right? And then I realize that it's because I have an ln x here. And ln x is only defined for x strictly positive. Right, here's our graph of y equals ln x. Only defined for x strictly positive. So x can only go to 0 from the right when we're talking about an ln x. Anyway, so as x goes to 0 from the right, what's happening here? We have a 0 here, and then as x goes to 0 from the right, ln x goes to negative infinity. So we have 0 times negative infinity. This is another indeterminate form. But L'Hopital's rule can only be used on 0 over 0 or infinity over infinity. So we can't directly use L'Hopital's rule on this. However, we can rewrite this kind of indeterminate form as 0 over 0 or infinity over infinity. For example, if I take this x squared and write it as a denominator 1 over x squared, this is the same. I've just kind of unsimplified it to write it this way. But now writing it this way puts it in the form of infinity over infinity. And so now we can use L'Hopital's rule. So our numerator here is ln x, and so when we take the derivative, we get 1 over x. And our denominator here is 1 over x squared, or x to the negative 2. So our derivative is going to be negative 2x to the negative 3, or negative 2 over x to the third. That's our new denominator. But now, before we go and plug in x equals 0, let's simplify. So dividing by this fraction is the same as multiplying by its reciprocal. This simplifies to negative 1/2 x squared, and now as x goes to 0 from either side, this is going to 0. So our limit is equal to 0. So let's just talk a little bit more about this type of indeterminate form. When we have a 0 multiplied by an infinity, we need to figure out which one is going faster. Is this function x squared pulling the product to 0 faster than ln x is pulling the product to negative infinity? And in fact, yes it is, because this limit is equal to 0. So now, so far, we've seen 3 types of indeterminate forms. We've seen 0 over 0 and infinity over infinity, and we can use L'Hopital's rule directly on these 2. Here, when we have 0 multiplied by infinity, or of course infinity times 0, we have to change to a 0 over 0 or infinity over infinity, and then use L'Hopital's rule. But there are other indeterminate forms as well. For example, infinity minus infinity. If we've got a function that's going towards infinity and we're subtracting another function that's going towards infinity, we need to figure out which one is going to infinity faster. If the first one's going to infinity faster, it might pull this whole thing to infinity. If the second one's going to infinity faster, it might pull the whole limit to negative infinity. Or if they're going at comparable rates, this might turn out to be constant. So this is another indeterminate form, and we're going to see in just a minute how we can handle this. But our method here is to get it out of the form of subtraction. So that might mean making a common denominator if we've got fractions. It might mean factoring. And we'll see an example where we even can use the exponential function to help us out of that situation. And we'll see that below. Also, we'll see an example of one of these. We have 0 to the 0, infinity to the 0, and 1 to the infinity that are also indeterminate forms. And for all of these, we want to use the natural log to help us find the limit. And we'll see an example like this below. Now let's take a look at an infinity minus infinity. So here we have limit as x goes to 1 over ln x minus 1 over x minus 1. Now we know that as x goes to 1, these denominators both go to 0. ln of 1 is equal to 0, 1 minus 1 is equal to 0. But when we have a limit with 1 over 0, we need to know in which direction we're going to 0, because remember, 1 over 0 from the right is positive infinity, and 1 over 0 from the left is negative infinity. So it's important to take a look at the direction from which we're going to 0. So we want to separate this into limit as x goes to 1 from the right and limit as x goes to 1 from the left. As x goes to 1 from the right, we know that all the x values are bigger than 1. So here's our graph of ln x. As x is going to 1 from the right, we're talking about ln values that are bigger than 0. So we're going to 0 from the positive side. So we have 0 plus here. Also, when the x values are bigger than 1, x minus 1 is going to be positive as well. So this is also 0 plus. As x is going to 1 from the left, ln x is going to 0 from the left, from values that are negative. So we have a 0 minus here. And same thing with x minus 1. When the x values are less than 1, this subtraction gives us a negative value approaching 0. So again, 0 to the left. So here we have positive infinity minus positive infinity. And here we have negative infinity minus negative infinity, which is negative infinity plus infinity, same thing, same indeterminate form. So to get around this, our goal is to get it out of the form infinity minus infinity. So here we have the subtraction of two fractions. We should make a common denominator. So doing that gives us limit as x goes to 1, x minus 1 minus ln x over the product ln x times x minus 1. If it's necessary for us to break up the limit into left and right, we'll do that again, but let's hope not, and at this point let's do our calculations as x goes to 1 with a two-sided limit. Now, since we got it out of the subtraction form, let's take a look at what happens when we just plug in x equals 1. We get 1 minus 0 over 0 times 0. So we have a 0 over 0, which is a type of indeterminate form on which we can use L'Hopital's rule. So we take the derivative of the numerator and derivative of the denominator, and we're here. We do a little simplifying by making a common denominator in the numerator and a common denominator in the denominator, and then simplifying this fraction, and then plugging in x equals 1, we still get 0 over 0. So we use L'Hopital's rule again. And now we have 1 over 1 plus ln x plus 1. So 1 over 2 plus ln x, plug in x equals 1, and this gives us 1/2. And so now we found our limit. So we started with a limit that was infinity minus infinity. Either way we looked at it, right? As x goes to 1 from the left or the right, we were getting infinity minus infinity. And we just changed the way it was written so that we can write it as an indeterminate form 0 over 0 and then use L'Hopital's rule. Let's take a look at another limit, infinity minus infinity. Here we have limit as x goes to infinity ln x minus x. So when we plug in x going to infinity, we get infinity here, so this is infinity minus infinity. Now I'm going to take you through a solution here using exponentials because I think it's a valuable tool and I want you to see it. And then I'll show you an easier way we can solve this particular example. So similar to what we do when we're taking the limit with a variable in the base and a variable in the exponent, we take the natural log of both sides. Here we're going to take the exponential of both sides. So we're going to call this limit y, and we're going to take e to the y equals e to this limit. And just like what we did with the natural log, we pull the limit through the natural log by continuity, we can do the same thing here. We can pull this limit outside of the exponential function by the continuity of y equals e to the x. So now we're here, and notice this infinity minus infinity now becomes a product here because we can write this as e to the ln x multiplied by e to the negative x. And so now we're looking for limit as x goes to infinity of this product. Well, we know that e to the ln x simplifies to x. And so here we have infinity times 0. We've seen this kind of thing. We want to write it either as infinity over infinity or as 0 over 0 so that we can use L'Hopital's rule. In this case, I think it's easiest to work on the e to the negative x and write that as e to the x in our denominator. Now we have this in the form infinity over infinity, and now we can use L'Hopital's rule. Keep in mind, the left-hand side of this equation is still e to the y. So we have e to the y is equal to, by L'Hopital's rule, limit as x goes to infinity, 1 over e to the x. As x goes to infinity, e to the x goes to infinity, and 1 over infinity goes to 0. Now, it's important to notice that this is going to 0 from the right-hand side, from the positive values, because the next step is to take the natural log of both sides. And we can only do that for values that are going to 0 from the right. So now taking natural logs, we have y approaching negative infinity. And this is the original limit that we were trying to find. We called it y. And using exponentials can be a very useful tool in changing a limit from subtraction to a product. But this particular limit can be solved in a quicker way. If we factor out an x from each term here, then we're going to have limit as x goes to infinity, x multiplied by ln x over x minus 1. Now, we still have subtraction, but we no longer have subtraction of infinities, right? Because this is now just a 1. So let's see what this limit looks like. We know as x goes to infinity, we're going to have an infinity here. But what about this limit? As x goes to infinity, what does ln x over x go towards? Well, we saw above that this limit is equal to 0. So this is going to 0, and this is going to infinity, and so we're getting infinity times negative 1, or negative infinity. So this is a bit quicker for this problem, especially because we took a look at this limit already above. Let's take a look at one more example. Here we have limit as x goes to 0 from the right, cosine x to the 1 over x. Now, I've mentioned in previous lessons that whenever we see the variable in the base and also in the exponent, we're going to want to use natural logs to deal with that. So that is definitely what we want to do here. We want to let y equal this limit and then take the natural log of both sides. I want to point out, though, that the type of indeterminate form we're looking at is 1 to the infinity, because as x goes to 0 from the right, cosine x goes to 1. And 1 over x goes to infinity. So this is a 1 to the infinity indeterminate form. So we let y equal this limit. We take the natural log of both sides. And again, we can pull this limit through the natural log by the continuity of y equals ln x. And so now we can take this 1 over x down in front of the log. So now we're here. We have limit as x goes to 0 from the right, 1 over x times ln of cosine x. As x goes to 0 from the right, we have 1 over x going to positive infinity. And as x goes to 0 from the right, cosine of 0 is 1, ln of 1 is 0. So we have an infinity multiplied by 0. So remember, we can't use L'Hopital's rule on this directly, but we can rewrite this in the form 0 over 0 or infinity over infinity, and then use L'Hopital's rule. And this is going to be a simple one to rewrite because we have a 1 over x here. So let's just write this product in quotient form. We have ln of cosine x over x, and we see that as a 0 over 0 indeterminate form. And so we use L'Hopital's rule on the right-hand side. And so ln of y is equal to limit as x goes to 0 from the right. Our derivative here is negative sine x over cosine x, and our derivative in the denominator is 1. So this limit is then negative of tan of 0, and so that's 0. So that tells us ln y is equal to 0, and then that means y must equal to 1. And so that's the limit that we were trying to find. And with this, we'll conclude our lesson on indeterminate forms and L'Hopital's rule.